Question 5a. A student carries out an experiment to determine the equilibrium constant for a reaction by colorimetric analysis. The production of the red-colored species FeSCN aqueous is monitored. A says the optimum wavelength for the measurement of FeSCN must first be determined. The plot of absorbance A versus wavelength for FeSCN is given below. What is the optimum wavelength for this experiment? Justify your answer. So, looking at the chart, I put that the optimum wavelength is 450 nanometers because when you look at the chart, that is the peak of it when it gets the highest and before it starts to go down. So that is the maximum absorbance by FeSCN. So B says a calibration plot for the concentration of FeSCN is prepared at the optimum wavelength. The data below gives the absorbances measured for a set of solutions of known concentration of FeSCN. So on the chart, they basically just gave us the concentrations, which is mole per liter, and then how much is absorbed in the mole per liter with those certain values, which are just given. So when we go to I, they ask to draw a Beer's law calibration plot for all of the data on the grid below, indicating on the scale of the horizontal axis by labeling it with appropriate values. So for the Y, I just put 10, 20, 30, and 40, which is just going up by tens. And then on the X, I just put values that were from the chart or values that were very close to the chart. And Beer's law states that it relates the attenuation of light to the properties of the material through which the light is traveling. So the same thing with that relationship between light traveling per moles per liter and the rate of which it's going. So once we graph these, we find that there are points a little bit underneath half of what is 0.10, so one about here. And then the next point is a little bit like 0.15, so here from the data given. And then the last one is a little bit more than 0.20. And then when you draw that, you should have somewhat of a straight line. Double I says that an FeSCN solution of unknown concentration has an absorbance of 0.3. Use the plot you drew in part 1 to determine the concentration in moles per liter of this solution. So basically all you have to do is go back to your chart, and they say that your concentration has an absorbance of 3, so you go to your 3, and you have to see what the concentration would be in moles per liter, which is your X. So you just have to match with the line that you drew, and when you finally match with the line, you should see that it is about one more than your last value, which I had as 15.0 times 10 to the negative fourth. So this is just an approximation, but it would be approximately one more, so about just 16 times 10 to the negative fourth moles per liter with the charge. Okay, so now that we've analyzed the chart and the data, the next part, C, is asking more about the direct equilibrium. So C says the purpose of the experiment is to determine the equilibrium constant for the reaction represented below. So then they give us the equilibrium reaction, and then it says write the equilibrium constant expression for Kc. So to write Kc is very simple. It is simply products over reactants. So then our products, FeSCN2 would be on top, and our reactants would be on the bottom. And since there's no number indicating the amount that we have in front of them, we assume it's 1, so therefore there is no power. It's not going to be squared or cubed or anything. It's just 1, because in the reaction we only are given 1 for each. So that's the final expression for Kc. Okay, so the next question says, the student combines solutions of FeNO3 and KSCN to produce a solution in which the initial concentrations of Fe and SCN are both 6 times 10 to the negative third molarity. The absorbance of this solution is measured, and the equilibrium FeSCN concentration is found to be 1.0 times 10 to the negative third molarity. And then it asks for us to determine the value of K. So for this one we have to make an ice chart, which is pretty simple because right off the bat they give us the initial values of Fe and SCN, which is written in the problem as 6.0 times 10 to the negative third. So I'm just going to put those there. And since initially we don't have any of this, because they don't say that we have it, it's just going to be 0. And then the next step is pretty simple because it's also given in the problem. It says that at the equilibrium, the FeSCN concentration is found to be 1.0 times 10 to the negative third molarity. So right then and there they give us the change, which is just 1.0 times 10 to the negative third. So then we have our C. And we're adding it to the 0. And then from there we have our initial and we have our change, so we can calculate the E. So for Fe it would just be 5.0 times 10 to the negative third molarity, and same for our SCN. And then for this one, it would just be 1.0 times 10 to the negative third molarity because we're adding it from 0. And now from there we can write our Kc. So once again, Kc equals products over reactants. So we have our products on top, which is 1.0 times 10 to the negative third. And then the bottom, both of our reactants, which are just both 5.0 times 10 to the negative third, which we can just write as 5.0 times 10 to the negative third squared. And then I already have this calculated, so when you put it in the calculator, you should get 40 as the final value. So the last question asks, if a student's equilibrium FeSCN solution of unknown concentration fades to a lighter color before the student measures its absorbance, will the calculated value of Kc be too high, low, or unaffected? And I said that the value of Kc would be too low. And why it would be too low is because the lower absorbance from the loss of color means that there is less FeSCN than there was before because of the fading. So the fading basically indicates that you are losing FeSCN. So since you're losing, it would be lower of FeSCN into the equilibrium expression, which would lead to a lower value of Kc.